This is the second day of section 3.2, and we will be graphing piecewise functions. Piecewise functions, as we had talked about in, I believe it was section 3.1, it is a function that is set up to include two different possibilities or more, could be three or more, where you have a different expression for a specific set of given values of x. And when we look at graphing these and not just plugging in values to analyze a specific value for x, we have to be a little bit careful. So we have here f of x is equal to either 1 or x minus or x plus 1. And f of x is going to be equal to 1 when x is less than or equal to 1. And f of x is going to equal x plus 1 if x is greater than 1. So what we need to do is we need to set up two separate tables for graphing. One for f of x is equal to 1, and the other one for f of x is equal to x plus 1. We have to pay attention to the inequality given to us. So we are starting at at x equals 1, and then we're going to choose all the values less. And so your table is going to be set up in a way to include those values, and what you want to do is get enough values to allow you to graph. And since we are graphing, we also have to be aware of the inequality. So if we have less than or equal, we will start the graph with a solid dot. Okay, and then for the other one, since it's just greater than 1, we will start that graph with an open dot. So we have to make sure that we are very careful and we pay attention to that information. When I look at f of x is equal to 1, and I have x is less than or equal to 1 for my values of x, since I'm going to start with 1 and then come up with values less than 1, I'm going to put my 1 down here and then go less. So 0, -1, -2, and that might be enough here. No matter what I plug in, my answer is going to be 1. And that's what happens when you have f of x equal to just a number. Your outcome, your y value, is always going to be that one number. So no matter what I plug in, I don't have to do any work here other than set up my table and put in my numbers for 1. So when I go to graph that specific graph, I would start at 1, 1. So 1, 1, and I'm starting that with a solid dot. So I might want to highlight here somehow, that I'm starting with that 1 and I'm setting up my table. I obviously wrote it down that I started with a solid dot, but since it's at the end of my table, it might be a little bit confusing, and I might think I'm starting at the -2, 1. So make sure you identify your starting point somehow, some way. It is very important. People get that confused very often. Now, if I plot all these other points, 0, 1, and these are all going to be solid dots too, but the fact that these are solid dots have nothing to do with starting with a solid dot. -1, 1, -2, 1, and then I could keep going on forever and ever in that one direction. So I'm going to start here with a solid dot, and my graph goes to the left, and that's going to go on forever, and I started here with a solid dot. Now looking at the other part of my function, I have f of x equals x plus 1. So here I'm going to start at 1, but again, I'm starting with an open dot. And then I go greater. So 1, 2, 3, 4. And again, I want to somehow highlight this open dot. Okay? And if I plug in 1 for x, I get 1 plus 1, which is 2. When I plug in 2, 2 plus 1 is 3. When I plug in 3, 3 plus 1 is 4. When I plug in 4, 4 plus 1 is 5. And now I'm going to plot these points. Now, again, I'm starting with an open dot at 1, 2. So 1, 2. That's an open dot right there. And then 2, 3. And these are solid dots from this point forward. Only the first dot is open. All right. 3, 4, 4, 5. So we can see that that's going to be a line. And let's see. And that's going to go like this. And we draw the arrow going on forever and ever in that direction. Okay, so vertically, if you look up and down, you should almost never have, you should always have like maybe one open dot and the other is a solid dot. I guess it's possible that they could both be open dots sitting on top of each other vertically like this, but they can never both be solid dots because that would not be a function. If we think about the definition of a function, um, we are told that the definition of a function is that for every value of x that goes into the function, there is only one value of y that associates with that value of x. So if I think about the value of x equal 1, right now I only have one value that associates with x equal 1, and that is y equals 1. So if I had both these filled in, then that would mean that at x equals 1, I have either 1 or 2, which is not a function. All right. So let's look at another example. We have f of x is equal to 3 different expressions, and we have 3 different sets of values for x. The first one is x is less than or equal to 0. The second one is the values between 0 and 3, where we do not include the 0, but we do include the 3. And then the last one is x is greater than 3. So I set up my 3 tables, so 3 separate tables because we have 3 expressions. And I'm going to, here, I start with a solid dot, okay? And I'm going 0 and smaller. So again, I'm going to start down at the bottom of my table, and I'm going to mark this um, clearly. And then I will go -1, -2, -3, -4. And when I plug in 0 for negative x, that would be -0, which is just 0. When I plug in -1, that's the negative that's given to me, and my -1, which is +1. So +1. When I plug in -2, that other negative is going to affect the value as well. So just like this, I have 2 negatives, so I get +2. So basically, it's the number I put in, and it's the opposite value. So -3 goes in. I wrote that wrong right here. Let me fix that. That's a +2. When I plug in -3, I will get +3. When I plug in -4, I will get +4. So it's good to see patterns, helps you get through the problem quicker. If I go ahead and plot this, I start with a solid dot at 0, 0, and then I go -1, 1, -2, 2, -3, 3, -4, 4, and so on and so forth. And I will draw my line in that direction. And I want to make sure I put an arrow at the end. I only go the arrow on one end of it because obviously I'm not going to the right of the 0 for x. All right, so f of x is equal to 9 minus x squared. Now here, at 0, I have an open dot. So I'm going to write it like this, open dot. And then at 3, I have a solid dot. So I have to be very careful when I'm doing this. So 0 is my smallest number, 3 is my largest number. So I'm just going to start here with 0, 1, 2, and 3. At the 0, I said that's an open dot. And at the 3, that is a solid dot. All right. And then I plug my numbers in. When I plug in 0, that's 9 minus 0 squared, which is just 9 minus 0. I get 9. When I plug in 1, 9 minus 1 squared, 1 squared is 1, and 9 minus 1 is 0. No, 9 minus 1 is 8. Don't know. I guess I was thinking ahead. When I do 9 minus 2 squared, 2 squared is 4, and 9 minus 4 is 5. 9 minus 3 squared, 3 squared is 9. Here's where 9 minus 9 will be 0. When I go to plot these, I get 0, 9. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, just barely enough. I get 1, 8, 2, 5, 2, 1, 2, 3, 4, 5, and 3, 0 is a solid dot. Now remember, I'm only going to stop there. There's no arrows on this one because I have a defined beginning point and a defined ending point. So no arrows on this part of the graph. And that's that part of the graph. And then here, um, there we go. We have f of x is equal to x minus 3 when x is greater than 3. So I'm going to start with 3 and count up. I start at the 3 with an open dot. So I'm starting here at the 3 with an open dot. When I plug in 3, 3 minus 3 is 0. 4, 4 minus 3 is 1. When I plug in 5, 5 minus 3 is 2. So you can see I'm just counting up by ones here. 6 minus 3 is 3, and 7 minus 3 is 4. And when I go to graph that, I have 3, 0. Uh-oh, that's supposed to be an open dot. Well, that's okay. Okay, since we're putting an open dot on top of a solid dot, no big deal. There's no conflict as far as this being a function. So we actually just leave it. We don't try to make this some kind of um, uh, mutated dot where part of it is solid and part of it is open. We're just going to leave it. So 3, 0 is already signified. Then we go to 4, 1. Again, these are all just solid dots because it's only the first dot that is affected by the inequality. 5, 2, 6, 3, 7, 4. You can see we have a straight line going off the other side here. And it's the other thing too is to pay attention to the expression that you're working with. Can you tell if it's linear, if it's quadratic, or whatever? So you kind of know what that part of the graph will look like. So when I look at f of x is equal to negative x, I know that's a linear expression because there's no exponent on x. So that part was a line. You can see it's a straight line. When I look at the second part of the graph, 9 minus x squared, well, x squared is a quadratic, and quadratics are parabolas. So it should have some sort of a curve, especially for the fact that when we look at x equal to 0, we actually had that involved. So that point right there would be the common vertex of this parabola. So if I were to graph that entire parabola, it would have a reflected image on the left hand side. So you're definitely going to have that pronounced curve that is at the beginning of a parabola. So that's something to be aware of. And then here, f of x equals x minus 3. Again, no exponent on x, and that's going to be linear. And you can see there was a line over here as well. So our graph here, it's kind of an interesting broken up graph, but that's, different parts have different meanings, for whatever you're analyzing or looking at. But piecewise functions are definitely used in business and sales and things like that. So the understanding of them anyway, yeah, not necessarily have to graph them all the time, but that's what we get. All right. And that is the second day of section 3.2 is basically just working with piecewise functions and being able to graph those.